In our first video on gases for this unit, I want to talk about what gases are and what it means to be an ideal gas, since we learned in pre-AP that ideal gases are very important. So some notes you might want to jot down, like, what is a gas? Just some vague terms that are very important. So the first thing, gases have a low density. They are the least dense state of matter, if you want to write it fully out. I mean, what that really means is that the particles in the gas are far apart. It's very important that you understand that conceptually, like on the AP test, that they want you to represent that with a drawing. You would draw it something like this to represent the particles being far apart, as opposed to something like this, which shows particles a lot closer together. That's more of a liquid or a solid. So gas particles are far apart. They are compressible, highly compressible. Liquids and solids are both considered incompressible, implying that you can't compress them at all. So gases, on the other hand, because you do have all of this open space in a sample of a gas, if you squeeze the particles, they'll come together some and use up, if you will, some of that empty space. That's why you can change the volume of a gas. Gases form homogeneous mixtures. Any mixture of gas, of any gases, if it's helium, neon, argon, they mix completely equally, homogeneously. Air is a homogeneous mixture of nitrogen, oxygen, argon, and some other stuff. So always homogeneous. And then also importantly, gases do not have a fixed shape. And they also do not have a fixed volume. This volume kind of goes back to what I said about being compressible. So very related here. We know that solids have a fixed shape and a fixed volume. Liquids have a fixed volume but a changing shape. And gases can change both shape and volume. It all goes back to the particles. Now, gases have to obey some set rules. These rules are set forth in what we call the kinetic molecular theory, or just KMT, kinetic molecular. That implies it has to do with motion and energy, so kinetic molecular. Depending on what source you use, you can get 4 to 6 postulates of the kinetic molecular theory. I have it broken up into 5. So the first thing the kinetic molecular theory tells us is that in gases, the particles are in constant and random motion. They're always moving, and they're not always moving in the same direction. That's what we mean by random. They do travel in straight lines. They don't just zigzag on their own until they hit something. So the meaning of random is that they're all moving in different directions instead of all moving in the same direction. The second postulate, it says that the particles are far apart. We've talked about that kind of briefly already. And this is important. No attractions for each other. This explains why they're far apart. If there were attractions, they would clump. We've learned these in pre-AP as IMFs. Intermolecular forces. Hydrogen bonds and such. The KMT tells us that gas particles are small. And I'm going to just summarize this here. Negligible volume. Now, that doesn't always make sense. So let's draw another picture. So if we have a box here with gas particles in it, let's just say this is a 2-liter box. And I have a gas. Well, if the particles were up like this big, then the amount of space that they actually occupy would be 2 liters minus the volume of particles. That's if they were big. But gas particles, we've already learned from number 1, or I should say, actually this one, number 3, is that they're tiny. Even tinier than what I'm showing here. So if you had another 2 liter box, and then you subtract the volume of the actual particles themselves, it's still right about 2 liters. Okay? Almost nothing is subtracted. So that's what we mean by the particles themselves have a negligible volume. The next one is that collisions are elastic. So the gas particles are all moving and zipping around. They're hitting the walls, they're hitting each other. What this means, elastic, is a physics term that means momentum is not lost. What we can simplify this to help you out, if you haven't had physics yet, is that no energy is lost. Okay? Elasticity really refers to momentum, but that is related to energy, and that's what we're going to go with. When gas particles collide with each other or they collide with the wall of their container, they don't slow down, they don't stick, they just change direction and keep going at the same speed. And then the final one I have is that temperature of a gas is proportional to its kinetic energy. So we use the Kelvin temperature as a way to describe how fast the particles are moving. If you remember from physics, kinetic energy is 1/2 mv squared. So the temperature goes up, the kinetic energy, we're being told the kinetic energy is increasing and the mass isn't changing, so that means the speed of the molecule is changing. So what does this earn you? If you do those 5 things, what do you get to be? Well, if you behave and follow those 5 rules as a gas, you get to be called ideal. So when I say the word ideal gas, really what I'm telling you is that I have a gas that does all of those things. It's very tiny. It doesn't have attractions for itself. It doesn't lose energy when it collides. It behaves ideally. In reality, it's not possible. The good news is, though, for gases, is that it is closely approximate. So for a lot of gases and a lot of conditions, you can use the ideal gas assumptions and you're not going to get a lot of error. That's very helpful. So what can we do? What kind of conditions can we operate under to keep gases in this ideal realm where they're mostly following these 5 rules? Well, we can't do anything with moles. That's just a number of particles, so that's not helpful. We can't really do anything with volume. If a gas is too big to start with, it never had a chance to be ideal, and there are gases out there that are just huge molecules. So that's not real helpful either. But we can adjust P and T. So the conditions to give us ideal. Now what these conditions do is allow gases to best approximate those 5 tenets of the kinetic molecular theory. We want to keep the pressure low. Okay? We want to keep gas particles far apart. We don't want to squeeze them. We don't want to take away their extra space. We don't want to make them collide more than they have to. We want to keep the pressure low. And for temperature, we want to keep it high. If we have a high temperature, the particles are really zipping around. When they collide, they don't have a chance for the IMFs to make them stick. They're more independent. So high temperature is a good thing. Well, what if we don't have these conditions? What do we have on our hands? We have what we refer to as a real gas. Now, obviously, all gases are really real gases. But things like helium is a very tiny particle, one of the tiniest in all of nature. It moves very fast as a result. It doesn't have a lot of IMFs because it's an ideal gas. Helium is like almost the perfect ideal gas, as close as we can get in nature, really. As long as we keep pressures low and temperatures high, helium is an excellent ideal gas. But some things, like some pharmaceutical gases or some insecticides that they spray, those molecules are huge. And you have to keep the pressure low and temperature high, because if you let them cool at all, they'll just form little droplets, and you've seen this happen in lots of gases, like aerosol sprays. When you spray them in the bathroom, for example, they condense really quickly. So real gases, what do we have rules for those? Well, kind of. Real gases, we can use the ideal gas law, but we have to make corrections. So the things that we have to correct for in real gases are the IMFs that they really have that cause the particles to clump, and their real volume. So we can't ignore the size of the particles. And there are gas laws out there. We're not going to do a whole lot with it because it becomes a little complex, but there are things like taking the ideal gas law and just adding a little correction factor. This Z right here is something called the compressibility factor. So that's something you can do very simple if you're messing with the pressures and don't have exactly the pressures that you would consider ideal. Or there's something called there's lots of different gas laws. They're called the equations of state. And let's not get too carried away, but I'll show you probably the next in line. It's called the van der Waals equation. Yep, the same van der Waal where we had IMFs. But the van der Waals equation is interesting. It has, if you take pressure and you insert this term here, AN over V squared, and then you multiply it times V minus NB, that's a minus sign there, and that equals nRT. Well, that sort of looks like the ideal gas law by the N, but what we really have is PV equals nRT. So what does this equation do for us, and why does it look so complicated? Well, these terms here are correction factors for the non-ideal behavior. In other words, a gas that we would use this equation on would be one of real gases that has one of these or both of these problems. This term here corrects for the IMFs, because if you have IMFs, you're going to be stickier. The particles are going to be stickier, and so they're going to come together, and they're not going to create as much pressure because you'll have fewer collisions as the gases clump, or the particles of the gas clump. This one here is a correction for the real volume if you have a huge gas. You find that when you take a gas, a normal gas, like let's say carbon tetrachloride, CCl4, if you put that in the gas phase, it's pretty heavy, it's pretty big. If you do ideal gas problems with that, you're only going to see about a 1 to 3% error in most cases. So you really don't have to worry about it. Now, if you become an engineer or someone that works with gases in other ways, like just research science, then these equations of state, where you have to use things like the van der Waals equation, and there are many more and many more complicated that make even more corrections, you have to use those because it would be a safety or an efficiency issue at that point. Now, the final thing I want to do is talk just briefly about this idea of temperature. And I'm doing this because this was a question on the last year's AP test, and they loved this relationship, so I feel like I need to introduce it now. We know the postulate 5 tells us that temperature is proportional to kinetic energy for a gas. So there's a couple of ways that we can represent that. We can say that the kinetic energy of a gas is equal to, and I want you to just take my word for this, because the derivation of this goes into some physics that we just really don't have time for. But it's a proportion, and it puts some more specificity on that proportion that I told you in postulate number 5. That it's proportional to T, but very specifically to 3/2 times the gas constant, and just gas constant here, sorry, not G, R would be the 8.314 joules per mole K version of the gas constant. So we're not going to plug into this stuff. I just want you to kind of see this and ultimately get to my point here. So we have this expression for any gas. The kinetic energy of any gas is 3/2 times R times the temperature of that gas. The more physics explanation for kinetic energy is 1/2 mv squared. Now, here's where it gets a little bit complicated for chemistry. Because when we look at a gas, it's not just one thing like a ball moving through the air or a cannonball like you had in physics. There's lots of them. So we have to take this, first of all, and we have to multiply it times Avogadro's number. So capital N in chemistry is always Avogadro's number. The 1/2 stays the same. The mass of the gas stays the same. But we don't really use V. We use U. And you're thinking, what the heck? Why do we all of a sudden have to use a totally different variable? Well, we have to go and understand what's happening inside of a container with a gas in it. We have all these particles, and these particles are moving around like the KMT tells us, but these particles aren't all moving at the same velocity. Some are moving fast, and some are moving slow. This is a very important concept for you to understand when it comes to the AP test and answering their questions. The bigger particles are moving slower. The lighter particles are moving faster if it's a gas mixture. But if it's a single gas, like helium only, there will still be a distribution of velocity. So we call this the mean free path, or the root mean squared. Actually, root mean squared is a better term, velocity for this. Now, I really encourage you to read this derivation in your book. It's on page 219 and 220 of the Zumdahl book. The Brown and LeMay book doesn't really cover this too much. But let's just set these two equal to each other. 3/2 RT, remember that's kinetic energy. And the other way to do it is 1/2 Avogadro's number, mu squared. And if we just rearrange it, I'm not going to go through all the steps, but if you just rearrange it, you get this root mean squared velocity is equal to the square root of 3RT over m. And that m, of course, would be, well, skip the step here. I should have done this. Let's go back to this. If we take Avogadro's number and we multiply it by the mass, that will give us the molar mass that we're so used to. So for any gas, you can just look up on the periodic table and get its molar mass, or it's a compound, you can add it up. So you're like, what are we doing here? Why do we care? Remember the main idea. Let's not get bogged down in all the details of this derivation. Main idea: in a sample of the gas, all the particles have a distribution of speeds, and here's where it comes to the fruition. Last year on the AP test, they showed a graph like this. This is what we call a Boltzmann distribution. This is number of particles. And the bottom could be energy, or it could be velocity, which would be the u. So let's actually do that. Let's put the u. So what this distribution does is show you kind of how many particles are traveling at certain root mean squared velocities. The hump, and actually statistically it's just to the right of the hump, is where your average would be. So that's what we would say, like the temperature would be for this gas, is where the average kinetic energy, the average root mean squared, would be. Now the question on the AP test last year said, what if I lower the temperature, what would happen? Or it might have said, if I raise the temperature, what would happen to the shape of this curve? So here's where I want you to understand. If I slow these particles down, the curve will shift to look something like, more like this. You have a taller peak and it goes in. As you slow everything down, you're going to have more particles doing the same thing. That again goes back to your IMFs and attractions and collisions and all that good stuff. Now, as I increase the temperature, we're going to see it swell out, and I probably made that hump a little higher than it should be. It probably should come something like that, but there'd be a definite difference between here and here. So this graph has become very important for you to understand. It's a temperature profile. It's a Maxwell-Boltzmann distribution. If you have any questions about this, come and ask me, but do read up on that section of your book starting on page 219.